In the previous episode, we derived metric structure from coherence variation. Distance was not assumed. It emerged from stabilized coherence above threshold. Directional variation in coherence induced structure that behaved like a metric. Now, we take the next step. If the metric is coherence-induced, what determines its shape? In classical geometry, curvature measures deviation from flatness, but flatness is not primitive here. Uniform coherence is. If coherence is constant across a stabilized region, then no directional change exists. If no directional change exists, the induced metric does not vary. If the metric does not vary, curvature does not arise. Flatness corresponds to uniform coherence, so curvature must correspond to non-uniform coherence. This is the central idea. Curvature is not introduced. It is the structural response to coherence gradients. Let's slow this down. In the previous episode, we defined distance as accumulated coherence variation. If coherence changes gradually and uniformly, distances behave predictably. But if coherence changes unevenly, faster in one region than another, then distance relationships distort. Objects that begin parallel may no longer remain parallel. Paths that seem straight in one region bend in another. That bending is curvature. Curvature is the failure of directional uniformity. It measures how gradients themselves vary. So if coherence varies unevenly across the stabilized regime, curvature must appear. This is not an extra physical law. It is differential inevitability. Now, consider what this implies. If geometry is induced by coherence, then curvature is induced by variation in coherence density. Regions of concentrated coherence produce steep gradients. Regions of diffuse coherence produce shallow gradients. Regions of uniform coherence produce flat geometry. The strength of curvature reflects the rate of change in coherence distribution. This reframes gravity. In classical theory, gravity is the curvature of spacetime caused by energy and momentum. In the coherence framework, curvature is the geometric manifestation of non-uniform stabilization. We are not yet writing field equations. We are identifying origin. Curvature does not arise because matter exists. Curvature arises because coherence is uneven. Now, consider matter itself. In earlier episodes, we described matter as stabilized topological coherence. Persistent clusters of coherence that resist refinement collapse. If such a cluster forms, it represents a localized concentration of coherence density. That concentration necessarily produces stronger gradients nearby, and stronger gradients produce curvature. So matter and curvature are not separate ingredients. They are two expressions of the same structural condition. Matter is stabilized coherence. Curvature is coherence variation. They arise together. No external interaction law is required to bind them conceptually. Now, return to threshold. Below threshold, coherence vanishes. If coherence vanishes, stabilization vanishes. If stabilization vanishes, no directional variation can be defined. If no directional variation exists, no metric exists. If no metric exists, curvature cannot be defined. Gravity does not weaken below threshold. It ceases to exist because geometry itself is undefined. This is important. It means gravity is not fundamental. It is conditional. It depends entirely on coherence stabilization. Now consider scale. At large scales, coherence variations may smooth out. Localized fluctuations average across vast regions. The induced geometry approaches uniformity. At small scales, coherence fluctuations may become intense. Gradients steepen, metric variation strengthens, curvature intensifies. This suggests something profound. Geometry may behave smoothly at macroscopic scales, but become unstable or undefined near coherence threshold. Breakdown of classical geometry would not mean spacetime is torn, it would mean stabilization weakens. Now examine symmetry. Is curvature symmetric in this framework? Yes, because it arises from variation of a symmetric structure. The metric was induced from bilinear coherence variation. Bilinear structures are symmetric by construction. Curvature inherits that symmetry. Nothing asymmetric has been inserted. Symmetry is structural inheritance. Now consider transport. In flat geometry, transporting an object around a closed loop returns it unchanged. In curved geometry, it does not. The difference reflects accumulated variation. In coherence terms, transporting along different refinement paths samples different coherence gradients. If gradients differ, the result differs. Curvature is path sensitivity in coherent space. This is a structural phenomenon, not a force, not an interaction. Now consider the relationship between curvature and energy. We are not yet identifying energy with coherence, but we observe something. If coherence concentration produces curvature and stable coherence clusters correspond to matter, then matter and curvature are linked through stabilization. Any theory attempting to separate them at origin would violate the coherence framework. They share a common root. Now step further. If curvature reflects variation in coherence density, then dynamic change in coherence must influence curvature dynamically. If coherence evolves, geometry evolves. This suggests that geometry is not static. It tracks stabilization. We have not introduced time yet. But we see that once time is introduced, curvature must respond to coherence evolution. Now, pause. We have derived metric from coherence gradients, curvature from variation of those gradients, matter as localized coherence stabilization. All without assuming spacetime as background. Everything emerges from threshold. Everything depends on stabilization. Everything vanishes if coherence vanishes. This is structural economy. Now observe something subtle. In classical theory, curvature is described by second-order variation. That is exactly what we have described. First-order variation produces metric structure. Second-order variation produces curvature. The hierarchy mirrors refinement depth. First stabilization, then directional change, then change of change. Structure builds level by level. Nothing jumps. Now we approach a boundary. We have geometry. We have curvature. We have matter as coherence cluster. But we still lack dynamics. We still lack direction. We still lack temporal order. Curvature describes static geometric distortion. But what governs change? To answer that, we must formalize time. Earlier, we hinted that causality arises from antisymmetric refinement order. Now, we must make that explicit. Because once time emerges, curvature becomes dynamic, and geometry becomes responsive. So the next step is unavoidable. We move from curvature to identity, from geometric distortion to persistent structure, from coherence density to matter itself. Because if coherence clusters exist, they must persist across refinement. And persistence implies identity. That is where we go next.